Okay, now I'm ready. Okay, so you know how to use these equations. We've done that before. One tricky bit is sometimes finding a vector for omega AB and alpha AB, and we can talk about that for a moment. But if I were you right now, if you have not yet done this, you should absolutely print out the equation sheets that I've told you are going to be given to you. Find where these are on the equation sheet so you're familiar with exactly where they are so that you can find them very quickly and easily when it's exam time. Okay, so let's talk about finding a vector expression for omega AB. So a lot of times in these problems, we've seen that they give us an angular velocity as like a scalar in radians per second. They usually don't give it to us as a vector. One reason for that is because it leaves it up to you to set the coordinates that you want to use for the problem, and then you need to write this as a vector relative to those particular coordinates. So what are some methods for figuring out how to write this as a vector? There's basically two different ways we've done it. Right hand rule. Okay, so right hand rule is usually when we're given in the problem, we're usually given, if we're given a set of axes and we're told, like maybe I have a cylindrical body and I'm told, or it's drawn in the picture that omega is going like this, then I can visually do my right hand rule. And my right hand rule tells me that my axis of rotation points in the direction of my thumb, which would be positive y direction, right? So here I can visually, by visual inspection, tell that omega equals 40 j hat radians per second by right hand rule. Now, this one was particularly easy because the axis of rotation aligned perfectly with a cardinal direction, right? But we saw at least one problem where that was not the case, right? What did we have to do in that case where maybe you have X, Y, Z, and or out in space somewhere, maybe you're told the point X1, Y1, Z1, and this is at the origin. And we're rotating, oh, crud, about this way. Yep.
You're going to multiply the angular velocity by a vector from the rotational axis to the point that you're looking for the velocity of.
Okay, let's see what that looks like. You're saying multiply your angular velocity times the vector that goes in the direction of my axis of rotation. So I still need to do right hand rule to figure out that my axis of rotation points this way, not down into the left, but up into the right. And so if we form an axis that goes from this origin to this point here, this might be like x1 minus 0 I hat plus y1 j hat plus z1 k hat. Is that it?
Yeah, yeah. Is that
right? So this is not a unit vector. This is not a unit vector. This is legitimately basically the position of this point in space. And so the magnitude is going to be the distance between these 2 points. And so if you multiply that somewhat arbitrary magnitude times your omega, you're going to get some overall magnitude that is not this 40 radians per second. That will be incorrect. So what you have to do is you have to turn this vector into a unit vector by dividing it by its magnitude. So in this case, omega equals omega times x1 I hat plus y1 j hat plus z1 k hat divided by the square root of x1 squared plus y1 squared plus z1 squared. Okay, so we just divide each component by the overall magnitude. That becomes a unit vector. Now we're happy. Okay. I think that's most of the big tricks here. Now tell me, this might be a little bit of foreshadowing. Let's say we had a rod that looks like this. And what if we had a collar? And maybe this is point C, this is point A, this is point D or something. Our point, so this is like a sleeve. It's like a thrust bearing, not a thrust bearing. Thrust bearing can provide thrust. It's like a bearing that allows rotation and translation. Okay, so this collar can move along this shaft AB. Maybe this is B. So can I use the equations I used above to relate the velocity of point A and point C?
Professor,
Yes.
I'm a little confused on the last one. So you can't use the right hand rule when you were like rotating it? It wouldn't like be pointing towards the origin for the angular velocity?
Here on
Yeah,
this second drawing,
right.
if you use right hand rule and your fingers curl in the direction of omega, your thumb points out into space, not in towards the origin.
Which way? But it looks like you're having to turn your hand like counterclockwise, isn't
This
it?
purple is going around the front of the cylinder.
Oh. Oh, okay. I think I just got it confused in a little bit.
Okay,
I'm sorry about
that's okay. Okay. The answer here is no. The reason is because of this particular word. Tell me not now why you cannot use those. Point C is not fixed to the same rigid body that A is on. Okay, so that's where we're going to cover this after exam 1. That's where those equations with the big omegas, don't worry about it. Okay, what's next?
Is general planar motion is or it could be on the test, right?
Yes.
Could we cover like an example? General planar.
Yes. Okay, so the way that I broke up general planar motion is essentially these equations that relate 2 points on the same rigid body that are doing general planar motion. These are the most generic equations you can possibly have. Now, what happens is they essentially simplify if you have a certain special case. So let's say you have a body that's there were a couple of simple cases that we talked about. We talked about fixed axis rotation. We talked about pure translation, and we talked about roll without slip. And there were some kind of special equations that went with each of these, okay? So I want you to think of the 2 equations we just covered. Those go with this picture. Rolling without slip, we get certain relationships about certain points on this body. So we know that the velocity of O is equal to omega R I hat. The velocity of point P is 0. The acceleration of O is alpha R I hat. These are roll without slip conditions. Okay. Pure translation, when we are purely translating, we know that omega equals 0, alpha equals 0, and all points on the rigid body have the same velocity and acceleration. Okay. Oh, sorry, I did that wrong. This was supposed to be up here. I said pure translation. Fixed axis rotation is, I believe, another equation on your equation sheet where the velocity of any point on the rigid body is equal to omega cross r p, where rp is the vector that goes from anywhere on the axis of rotation to point P. And then acceleration. I forget what I give you for acceleration. It's on the equation sheet. Can someone pull it? Well, I guess I can pull up the equation sheet.
It's or alpha.
Is it just
it's
alpha cross R?
RP plus omega cross omega cross RP.
Okay. So alpha or acceleration of P equals alpha cross RP plus omega cross RP. Okay, so what you should be noticing is for instance, that this is, let's look at our general planar equations. Let's go back to our general planar equations and prove to ourselves that this agrees with a simplification of that. Let's go down here. So this one is general planar motion. And this one is fixed axis rotation. So what we'll do is let's take a body doing fixed axis rotation. And let's say I want to relate a point on the axis to some point P using my general planar equations. I would write that acceleration of P equals acceleration of, we'll call this maybe A for axis, plus alpha A P cross R P slash A plus omega A P cross omega cross R P slash A. What is the translational acceleration of a point on the axis of rotation? Yeah, because that point is just staying where it is because that fixed axis is fixed. Okay, so this goes to 0. RP slash A is by definition the vector that goes from a point on the fixed axis to the point in question. So in all actuality, this is the same as RP. And we arrive at our fixed axis equation. Does that make sense? So when we talk general planar motion, it's really these two equations are the most important, and everything else is a simplification of that. Right? But you can even convince yourself of like pure translation, right? If omega goes to 0, that entire cross product goes to 0. If alpha and omega goes to 0, almost everything on the acceleration equation goes to 0, and we get VB equals VA. No matter what 2 points, they have the same velocity. And acceleration B equals acceleration A. The only one that's a little bit strange is fixed axis, or is rolling without slip, and that one you just have to memorize. VO equals omega R, acceleration O equals alpha R, and then the velocity of the point in contact is 0.
Also, this might be like a silly question, but.
I love silly questions.
Do vector bars, like if we forget to put those, would that be points off?
It wouldn't be points off, but it will make it harder for me to figure out partial credit. But it's not like you forgot the arrow minus a point.
Okay,
It's like if you forget that it's a vector entirely and you're trying to do the problem without treating it as a vector, that's a bigger problem.
but if in our work, like we do it as a vector, but we just
Yeah.
forget, okay.
Robert, did you have a question?
For the roll without slow motion.
Yep.
During the review, you were
Mhm.
saying at the top, it moves twice as fast, the bottom is kind of still.
Mhm.
And that makes sense logically, but you said it wasn't just logically, it's going forward faster. What is the actual proof of that? Is that
Yeah, it is. So basically what they wanted you to do was if you have a point that's rolling without slip, and this is point O and this is point P, and you have an R, they wanted you to use this general planar motion equation. You know that the velocity of O is equal to omega cross R. No. Yes, omega R in the I-hat direction, as long as I give you an I-hat direction, right? So you know this part. You need to use this equation to relate point O to some point at the top, maybe T. So we can say velocity of T is equal to the velocity of O plus omega cross R T slash O, where the velocity of O we can put in as omega R I hat. This will be, if we're translating to the right, that means that omega must have been the minus k hat direction. Right? If we're going this way, that's what would cause us to translate to the right. I'm assuming right word translation. Cross, the vector that goes to T from O would be R J hat. Whatever that comes out to, it probably is very similar to the disk being twice as large. However, the circumference hasn't changed. So the reason I said I don't want you to think about it as pretending that the disk is twice as big as it actually is because that would change your radius. Right? So that's why I said that during the review. So think of it like this, not pretending that your disk is something other than what's shown.
Dr. Higgins, are you still planning on posting the Jeopardy review to Canvas?
That has been posted.
Okay, thank you.
Yep.
I have a question on the first problem of homework 3 for the truck pulling.
Yeah.
The rope block. When doing the chain rule part of it, where you have to do the derivative there.
Yep.
You're supposed to end up getting a certain like variable on the top of the when you by having one, I just wanted to walk through the
Okay.
chain rule.
Yeah. Sure. Okay, so we're trying to take, I'll cover this, I'll uncover it once I get it rewritten. We're trying to take d dt of the square root of x d squared plus 5 squared. This. Yeah? Okay. I don't like to look at the root sign. I'd rather try to think of it as to the 1/2. Yep. Okay, so this is not just a single chain rule. This is actually two different chain rules. And the reason I say that is because XD is also dependent on time. Right? Because the truck is moving to the right, so XD is going to change over time. It's a function of time, which means that when we take a time derivative of this whole quantity, I can't just pretend like XD is the variable that I'm taking the derivative with respect to. I have to keep in mind that I'm taking the derivative with respect to time. And because XD changes with time, I'm going to have like that very last piece where I multiply everything by dxd dt. I think that probably is, but wait, let's do it together, okay? So my like outer shell is that I need to first take the derivative where I do 1/2 xd squared plus 5 squared to the minus 1/2. And then I need to multiply that by the derivative of the inside, which would be 2xd times the derivative of the inside of that, which is taking the time derivative of xd. So what we get then is 2xd xd dot over the square root of xd squared plus 5 squared.
Use cancel out, no?
They do. Yeah. Sorry. Does that help? Okay. What's next?
I have a quick question as far as cross products go. So, for example, I cross J, J cross K. What would you recommend we do as far as memorizing what the cross products of those would be? Would it be right hand rule or should we memorize the directions?
So some people draw this picture. And the direction here tells you what's positive. So if you take I cross J, you get a positive K. If you take J cross K, you get a positive I. And if for any reason you need to go in the opposite direction, it's negative. But to be honest, I don't ever memorize that. You don't need to if you do cross products the way that I've shown in all our notes, which is where you build that array, right? Like if I have A equals 1i plus 2j plus 3k, and I have b equals 2i plus 3j plus 4k. The way that I fill out this array is I write I, j, k, and then I write my a vector, which is 1 in the I hat, 2 in the j hat, 3 in the k hat, and then I write my b, which is 2 in the I hat, 3 in the j hat, 4 in the k hat. Okay. And then the result of my cross product is going to be something times I hat minus something times j hat plus something times k hat. And what goes in each of these blocks is what I call a forward product minus a backward product of little subchunks of this big array. So for I'm looking at this square here, and I do 2 times 4 minus 3 times 3. So I say forward minus backwards. So 4 times 2 minus 3 times 3. That's my I hat component. For the j hat component, I'm looking at an array formed by these two columns, and I have forward minus backwards. So 1 times 4 minus 2 times 3. Oh, sorry. And then lastly, for the k hat component, I'm looking at this part, forward minus backwards, 3 times 1 minus 2 times 2. That's my cross product.
That helped a lot. Thank you.
Okay, great, cool. Robert, were you about to ask something?
Yeah, for the one up before, instead of doing it directly, where you just took the derivative of the square root, if you first broke it down and actually got the position formula for the drop, and then kind of, I did it in a convoluted way, but I think
You
I-
tried to substitute in so that you only had t's in this expression.
Would we lose points for doing it that way?
If you get the correct answer, I'm not gonna take off points. But I would definitely prefer that you know it this way, and the reason I say this is because this class, it doesn't get too bad. In advanced dynamics, you'll start to talk about mechanisms that are made up of like chains of things rotating relative to one another. And you're gonna have to do chain rule after chain rule after chain rule after chain rule after chain rule. And it's just not gonna be feasible to do it your way. So I want you to get comfortable with knowing how to do the chain rule appropriately. Okay. And in fact, Robert, because you're interested in my robotics research, this is one of the like canonical models of a serial chain manipulator. So those robots that you see on the industrial floor that do a lot of like pick and place stuff, this is generally how we model it. Those robots are made specifically so that they are revolute joints or pin joints that each have a motor. There's a torque at each one of these. And like the intro to robotics stuff is all about how to control one of these. So it's not just some fairy tale, when will we ever see something like that? It's like this model forms the basis of a lot of different robots. So all this to say that you can't get away from chain rule, especially if you're interested in robotics. Okay, what's next?
There are some questions in the Zoom chat.
Oh, I'm sorry. Thank you for letting me know. Can we cover roll without slip? We did cover roll without slip, Dane.
That was earlier by like 30 minutes, to be fair.
Oh, okay. And then people keep asking about definitions. So this is my response. The first page of the exam is gonna have like a small handful of multiple choice concept questions. And then the rest will be work through problems that look more like homework problems. That's it. That's the exam.
Could I ask if those multiple choice questions will be kind of similarly worded to the ones in Jeopardy? I know they weren't multiple choice in Jeopardy, but they were conceptual, I guess.
What have you done in my class that is multiple choice?
Nothing, but I mean, like those kinds of.
Nothing. Have you not come to a single class?
Oh, yeah, yeah,
Woof. Okay, yeah, bell ringers. Yeah.
okay.
They're gonna be kind of like bell ringers. Where is the roll without slip equation in the equation sheet? To be honest, I'm not sure if it's in there. But if there's like one thing that you memorize, I think I can trust you to memorize that V of the center point is omega R in the horizontal direction. A equals alpha R in the horizontal direction. That's roll without slip. V of the contact point is 0. Bless you.
Thank you.
Yep, you're welcome.
Would you be able to explain? I know the difference between displacement and distance, but I remember back to, I want to say kinematics, there was a problem where basically the particle is moving left
Yep.
10 meters and then it switched direction. And you
Yeah.
needed to find the displacement and distance. What would be the difference in how you'd solve? Would one be an integral, or would both be an integral, but the way you go about the bounds be different?
You're asked two different things, displacement versus distance traveled. So displacement is final position minus initial position. Okay, so it ignores everything that happens between the two. So if you have a particle that's moving along this axis, and this particle starts here, and it goes this way, and then it turns back this way, and it stops here. This is your displacement. But your total distance traveled is the entire length of this green curved line, right? It goes from here to here, plus here to here.
And then when you take the integral, depending on what the certain times are, would you split up the integral for distance? I
So
guess what I mean by that
total
is,
distance traveled is not an integral. I think what you're referring to is the fact that you had to take an integral to find the position as a function of time.
yes, and then I think you plug in your time bounds to find the distance.
So you had to figure out at what point did you change direction? What time did this happen at? So that you could figure out where were you at time 0, where were you at time where you were turning around, and then where were you at this other time? Because you need to know those 3 positions in order to find the length of this plus the length of this.
So the goal would then be to find when velocity is 0.
That's the point where you turn around, yes.
Okay, gotcha.
Because if you're moving to the right, the way that I have this arrow drawn, that would be a positive velocity. If you're going to the left, that's a negative velocity. And so the only way for you to go from a positive velocity to a negative velocity is to cross velocity equals 0. So you know the point where you turn around is when velocity is equal to 0. And you had to solve for that time before you could find total distance traveled. But the total distance traveled in and of itself is not necessarily an integral.
Gotcha. Thank you.
Does that make sense?
Mhm.
Okay, great.
Can you briefly explain on the Jeopardy general plane motion 400? It's like the rigid body with like the 2 rollers on the sides. It's like slide 49.
This one?
Yeah.
Let me just draw it and then we can do it together.
So velocity and acceleration of just because like
Yep. Okay. So find V, B, and A, B at instant shown. Is that right? Okay. So my first thought is that these are 2 points on the same rigid body. These are 2 points fixed to the same rigid body. So my first thought is to go grab those equations. Let's do velocity. I think probably the part that tripped a lot of people up was the fact that we know that B is rolling on this like slanted surface. and it's gonna stay in contact with that surface. We can just assume that. So what happens is we know the direction of the velocity of B, but we don't know the magnitude of the velocity of B. And so we need to go ahead and incorporate what we know about the direction of that motion into the equations that we're finding. So what I would maybe think about doing is saying that I know that this is VB. And if you're not comfortable with 3, 4, 5 triangles, I forget what is the angle? Is it 30, 60, 90? I forget. We can take the tangent, like tangent of 4 over 3, tan inverse of 4 over 3 for me.
53.1.
Okay, that's gross. Okay, but we can use that to do our trig. Right? Do we agree that's that angle? Okay. So I can do that. I know VB goes some amount down. This will be the Y component, and some amount to the left, that'll be the X component. So I can go ahead and write on the left-hand side of this equation, this is VB, sorry, we have to give ourselves a coordinate system. Minus VB cosine 53.1 I hat minus VB sine 53.1 J hat equals everything on the right-hand side. So VA plus omega AB cross R B slash A. Now, I assumed it was going down. It may not be going down, but I'll end up getting a negative for what VB is. Does that make sense? So why is it necessary that we do this? Well, when I write it in this way, I'm only left with one unknown, just that magnitude VB. Whereas if I had not done this, the only way I could have written VB is that I would have some VBX in the I hat direction plus some VBY in the J hat direction, and those would be two unknowns. I would have some unknown amount in the X and some unknown amount in the Y. And I would end up with too many unknowns and not enough equations or relationships. Okay, so you have to leverage every piece of the information that you know. And that's how we incorporate the fact that I know which direction B is rolling. So then VA is given to me. That's purely up 3 J hat. I don't know omega, but this is a 2D problem. So I know it either has to be positive K hat or negative K hat. So I'll just assume one direction, and if I get a negative, that's what it means. And then R B slash A is the vector going from A to B. So this looks to me like minus 3 I hat. Okay. The other thing we need to get really comfortable with is looking at what I've just written and recognizing that this is two equations and two unknowns, which makes some people uncomfortable because there's only one equal sign. But these are vectors. So I can set the I hat components equal to each other and then the J hat components equal to each other. And so I then, within this same expression, I really have two separate scalar equations, which means that I can solve for the two unknowns that are there, that VB and the omega. I'm happy because two equations, two unknowns. Okay, so let's do that. So, whoa, gross. Actually, let's go ahead and do this cross product. I, J, K, 0, 0, omega AB, minus 3, 0, 0. I minus J plus K. Okay, forward minus backwards, that's 0 minus 0. forwards minus backwards, that's 0 minus -3 omega AB. And then K hat is forward minus backwards, that's 0 minus 0. So I have 3 negatives, minus, minus, and minus, so I should get -3 omega AB J hat. And now I can write my I equation. On the left, my i's are minus VB cosine 53.1. On the right-hand side, all my i's are gone because I only got a j as a resultant of this cross product. So this equals 0. I can already tell you what velocity of B is. It's not going anywhere. Instantaneously, it's not moving. Okay, but if we want to solve the acceleration part of this problem, we'll need to know what omega is. So we need to go ahead and write the J expression as well. So the J expression will be minus VB sine 53.1 equals 3 minus 3 omega AB. VB is 0, so this goes to 0. So this should just be 3 omega AB equals 3, so omega AB equals 1 radian per second in the K hat direction.
And you should do the same thing for acceleration.
Same thing for acceleration. And you have to do the same thing, the same song and dance with the direction of acceleration for B. Does that make sense?
Yeah, does this only work because it's like directly like horizontal? Like if it was slightly like up, would that like, change it? I guess that's where I was getting stuck on, is that like trying to visualize it, not like, so it's point A is like pure, it's pure rotation around B, but I don't know, I just got stuck on the fact that like only A would be changing it, whereas B is just.
You're saying it's confusing to you why VB equals 0?
Yeah, I guess just trying to think about like in this situation, like it actually physically happening, I guess it can happen.
It's very hard to visualize because this is only instantaneously true.
Okay.
What is very likely is that at like anything outside of this instance, VB is something else,
Okay.
right? So that's what makes accelerations are terribly hard to visualize. Velocities and positions are fairly easy to visualize. Accelerations are hard. And this is what makes statics so much easier than dynamics, is because as soon as you add acceleration into anything, weird stuff happens. That's just very difficult to visualize. Statics is almost like purely visual. It's beautiful in that way. It's very visual. You can draw vectors. Acceleration is just weird. Robert?
If we just use the problem that A is not moving left to right at the end, right, only moving vertically.
Yes, because you're given these vectors that point directly up. VA is up.
Knowing that, could we make the assumption reasonably that B can move and then solve it as a rotation? Because if you were to move B up or down, FA would have to shift left or right.
I don't want you to make any. The moment people try to do things visually, they get it wrong. I don't care whether it's right or wrong. You might be absolutely right, but I don't want you to do it that way, because inevitably it just is not foolproof. Accelerations are weird. Let the math handle it. Okay? Anything else? We got like 8 minutes left.
I have a question.
Oh, sorry, hold on, Samuel. I
Yep.
think, yeah, okay, Giovanni.
I think it's question 2 in the homework 2. Notes the numbers 12-179.
Okay. I should pull up the actual assignment. Okay, yeah. Mhm.
Yeah, I just want to make sure that this is those cases where, since the data dot is not given as a function of time,
you have to relate it by using the chain rule. Because we have the R, but that's not a function of time, so we have to relate it using the chain rule. But there's gonna be two theta dots, because you're looking at two different things.
Okay, you're getting those instructions slightly mixed up. So usually what the problem is that we need to take a time derivative of R.
Yeah.
Yeah, and R is not a function of time. R is a function of theta. And this problem doesn't actually give you the function of theta. It only tells you that at this particular instant, theta is equal to 2/3 pi. So in order to take the time derivative of R, you will first have to figure out a time expression for theta, which you absolutely can do because it gives you that theta dot is constant. So you can integrate theta dot to find theta as a function of time, and then you can find the time derivative of R, because you have to know theta as a function of time in order to do that chain rule. Do you want to do it together?
Sure.
Okay. Okay, so R equals 10 plus, I'm just gonna do the sub part that I just explained. I'm not gonna do the rest of the problem, so theta to the 1/2. And we know that theta dot is 1.5 reams per second constant. Yep, I just need to copy the problem. You're fine. Thanks for the reminder. There you go. Okay, so I'm aiming to take dr dt, but R is a function of theta. So I can't straight up do dr dt. I need to do dr d theta times d theta dt. Okay, I can take dr d theta. That one's easy. That's just the derivative where I'm treating theta here as the variable. So I should get 25 theta to the minus 1/2, I think. Is that right?
Yeah. Yeah.
Okay, but I'm not given theta as a function of time. It would be wonderful if it said something like theta is equal to 12t plus 4, and then I could say theta dot is just 12, but it's not, right? I have that d theta. Oh, shoot, wait. I don't even need to do it. You have theta dot.
Yeah.
You don't need theta as a function of time. Theta dot is always, always, always 1.5. So it's just take 1.5.
Yeah. It wouldn't be possible to do the problem if you weren't given that, though.
Correct.
Yeah.
Yeah.
That was my question, because it was on the textbook, and I was like, that's definitely that example, but I couldn't figure that out when I was doing the homework.
Yeah, the going back and forth between the dot notation and the d thetas, dt's, and writing out the chain rule. I know in the previous problem where it was chain, I didn't write it out as like this. We could have, but because there's like, I would have to make all of these different function names, and it would be just more complicated. It can be hard to remember how all these things are related.
Yeah, because then it also gives us the like the instant as a theta. So then you would plug in that into the other one. That's what I'm saying, like.
If you wanted to know what is R
Yeah.
at the instant, you solve that this is the expression for any theta. And then if you want to know what is it when theta is 2/3 pi or whatever it is, then you plug in that value for theta. Yeah. All right, Samuel?
All right, I'm pretty sure I understand the reason, but on the last problem, you made the components of V negative, and
Oh,
it
yeah,
doesn't end up mattering for this problem,
it
but
doesn't.
as long as they're both negative or both positive, it's right, correct?
So it all comes back to the fact that I drew it this way. Oh, why is it highlighting in black? I drew it this way.
If it was up and to the right,
And
they'd
if
both be
I had
positive.
gotten the negative out, I just would have known that it pointed the other direction. It
Okay.
points that way.
Okay, that's what I thought. Thank you.
Yep, you can assume either way. Whoops, sorry. 3 minutes. Anyone else? Who's administrator? Is that a student? I hope that's a student. Oh, did they? Oh, okay. Any other questions?
I got a really quick one.
Yeah, great.
So for the problem that you just did from the Jeopardy review, is
Uh-huh.
the distance of B relative to A -3 because you're using B as like the origin? So like it's like 0 - 3.
It doesn't matter where you put your origin, and I want you to be careful with the way that you said that. So it's not a distance. A distance is necessarily a scalar value. And this is a vector. So this is the vector that points from A to B. Okay, so this is, if I were to draw R B / A, I would draw this vector. The vector 2B with respect to A. And that vector moves exactly 3 feet only in the left direction.
Okay.
Does that make sense?
Yeah.
Okay, good.
On the question on the 12,179 you just did on the homework, and the actual answer, it kind of just disregarded the thetas, because it's asking about just the bar.
On the homework?
Yeah.
Oh, yeah. Yeah.
Is that just because it's only, like, you're only looking at the rod, so the rod's not gonna have any?
Yes.
Yeah, that's
So
what-
So here's the tricky thing about this problem is that usually the path is fixed in space. The path is fixed and the particle moves relative to the path. This is the opposite. They're asking you about this particle, which is fixed except moving left to right, while the path rotates through space. So yes, you have to recognize that based on the way they've defined the radial direction and the way that this rod is oriented, this particle can only move along the radial unit vector. So the only thing that matters is the radial unit vector. And we're at time, so we gotta go. Cool. If any other questions come up, please feel free to email me. I'm happy to respond to emails. Best of luck studying, and I'll see you tomorrow. You're welcome.
Thank you, Dr. Higgins.